Alright, hell yeah. So we got Problems in General Physics, and this is by Igor Irodov. You know what I mean? One of the subscribers was like, hell yeah, can you do every problem in the book? You know what I mean? And I was like, well, let's do the first chapter. We're on problem number 4. That's pretty amazing. And we did hella long videos on the first 3 problems. But this one, heck, we can do it pretty fast. And so what we're going to do, so we got to figure out what this is. It's a graph. This is distance, and it's in meters. So cool. Distance in meters. This is time in seconds. Cool. And what we know about like integration is if we have something like that, time and well, this one's just meters. It's kind of interesting. So usually what we have, let's do what we usually have. We usually have like velocity, that's going to be in meters per second. And then we have time in seconds. And then we usually have this. We're starting with 0 velocity and going up to, I do the problem, we go up to like 60. Well, if I guess we're doing meters per second, well, what is 60 miles per hour? Isn't that about 30 meters per second? We just divide by 2, we get pretty close. Okay, and in this scenario, hey, our average velocity is going to be kind of halfway. We can just see that. If we go from 0 to 30 meters per second, velocity average is going to be 15 meters per second. But how you would do it using integration is you'd find the area under the curve. So this distance right there, well, hell yeah, is 30 meters per second. Those are the units on that height. And then this time value right here, we haven't really specified. But let's say we're only going to do this for 10 seconds. Cool. So how far would we go if we're going an average speed? And if we're going an average speed of 15 meters per second for 10 seconds, heck yeah, we got a pretty good understanding that we're going to go 150 meters. But using integration, we would say, well, I just want to find the area under the curve, and the area of a triangle is the area of a rectangle divided by 2, or just 1/2 that. So the area of this full rectangle is going to be 30 meters per second, and then times 10 seconds. Seconds are going to cancel, and that's the area of the full rectangle, so we got to half it. So we're going to have 300 meters, and then half it gets that 150 meters. So we can use, well, I guess right now we're just showing that the area under the curve actually is something tangible, and it's this value, meters per second, this way, and then multiplied by this value in the x-axis, that's seconds. And when we do that, we get a term that's in meters, distance for that one. What happens if we take this axis, which is in meters, and then multiply it by seconds? Oh damn! Is this one of the problems where I'm just like I thought I knew exactly what the hell's going on, and then but this is the check on reality, because I'm doing these videos from total scratch, and my MO is to make a problem simple so you can find mistakes. But I think I found my first mistake. In this scenario, we multiplied meters per second times time, and you get something normal. You get meters, But if we have meters and seconds, if we multiply those two together, we get a term that no one's ever done before. Distance time, that's nonsensical. So what would we need to do? So there's two. If you have a graph, there's 2 things you can do. You can find the area under the curve. It's basically calculus. Calculus is 2 things. Good thing it's not 3 or 4. But you can find the area under the curve, and that gives you that representation. I'm glad I did that, because it proves that's not what we're going to be doing. Or the other thing that you can do is you can find the slope. So if the slope of right here is 0, and then, so you definitely have to write the equation for slope. I'm going to say m, because it comes from y is equal to mx plus b. This is the equation of a line, So if I have an equation, so if this is my line, y is equal to x, well, it looks like, the b part goes right through the origin, so that's 0. And then the m part, well, it must be 1. You can always throw something there. So, and so we have a slope of 1. Now, what is the definition definition of slope. Just always just, I think no one needs to remember this, but rise over run. It's always rise over run. But what you actually do, because, if you're on an x-way graph, it's just so easy to be like, well, to get to this point, I'm going to go this way first and this way. I think it's how we read books. We're always going to go from left to right and then maybe up to the point. I don't know. Just in a graph, that's typically what I do. But when this says rise over run, yeah, it's cool to get to that point that way, but you have to say, you got to do this rise part first. So, go this way to get to that point, but then, go the opposite way. We're going to rise 2, and then we're going to go 1, 2, 3, 4, 5. So, and this is just going to give us an average velocity for the first 10 seconds. And you can see that that's a horrible, horrible guess. And I even just spoiled it because I already kind of knew what was going on. What are the units on this? So what are we rising? We're gonna, so if we find the slope of that line, which isn't, the slope is way the hell down there, but we're just gonna say this is 1 meter. So what do we get? 0.2 meters, 0.4, 0.6, 0.8. So we're gonna do 0.4 meters. In 10 seconds. Cool. So the slope of this line actually gives us the velocity. So 0.4 divided by 10, and we get a velocity of 0.04 meters per second. Cool. So yeah, that's interesting. I thought the area under the curve would get that is interesting. Is some, because I was going to talk about that because sometimes you would have a relate, because this is velocity in time, but hey, you might be wanting a velocity equation with respect to position. You know what I mean? And I forget what the velocity equation is for that, but it's something, and then you got position. You probably got a square root or something, and so if I throw in a position, hey, I get velocity. So there you go. So maybe if I'm jumping off a cliff, my position right here is 0, but right here it's not 0, and I definitely have some sort of velocity. And we know that jumping off a cliff, if this is, how do I want to do this? I want this to be my velocity in the y, and this to be my position in meters in the x. So this is meters per second in the y, and I know position of 0, not moving. But even just position of 1 feet, I'm still not moving. You know what I mean? It actually takes a while to actually get up to some speed, but once I do, holy Toledo, jumping off a cliff, you will do something like this. You know what I mean? So that's a good representation. Now, if we did this, well, what's the area under this curve, and does it mean anything? Well, no, because we have meters per second times meters. You know what I mean? Whoa, we got meters squared per second. So that's a useless term. But now, since we have calculus, I don't know. I'm just on the fly. What is the rise over run? So the rise is in meters per second. And then the run divided by meters, well, this still is kind of nonsensical. We would get 1 over time, 1 over seconds for the slope of this. So there's an equation where maybe both the area under the curve isn't useful, and really the slope isn't necessarily useful. And the slope of anything is just the change in the y value. If this is the y and this is the, it's the change in the actual equation. So change in y divided by change in x. So it's going to be the change in the actual velocity equation if you move x just by a little bit. So explaining that is right down here. If we move x just a very tiny amount, well, our velocity didn't change at all. The second we jump off a cliff, for just a couple inches down off the cliff, we're still not moving. You know what I mean? It takes a foot to actually generate a tiny bit of velocity, and that's what we see. So our slope is very low, but holy Toledo, upon impact, between the last 10 feet and hitting, hey, our velocity might increase a huge amount in that last 10 feet. If these are 10 feet increments. All right, sweet. So that's kind of an understanding there. And the slope of this will give us the velocity at any given time. So we can say, hey, initially our velocity is 0. And then up here at time 20, our velocity is 0. So cool. So a velocity at time 20 is 0 meters per second, and our velocity at time 0 is 0 meters per second. And it look at this. This part looks like the steepest, and we're still kind of guesstimating because it kind of curves right in here, but that's cool. You know, we can just say from here to here, it looks fairly linear. So I'm just going to say that's linear. And we have 1, 2, 3, 4, 5, 6, 7. I think it's 7 times 0.2, which is 1.4. You know, is that what we get? We go up to, this is 1.8, 1.6, 1.4, 1.2. Cool. So we go 1.8 minus 1.4. Did we do that right? Yeah, it's 1.4. So our rise, so from here to here, our rise over run is going to be 1.4 meters. And how long did that take? You know what I mean? 10 seconds. What are these? This is 2, 4, 6, 8. You know what I mean? 12, 14, 16, 18. Really good to actually get numbers on that so you don't get confused. And we got 2, 4, 6. So we have 6 seconds. So we're doing that in 6 seconds. So our velocity, if it was 1.4 meters, if we did that in 1 second, you know what I mean, this is what that line would look like. But it's going to be a little bit slower than 1.4 meters per second. So it's 1.4 divided by 6, and we get a speed of 0.23 repeating meters per second. All right, hell yeah. And I thought if this was if this definitely was meters per second and this was time, well, hell yeah, integration under the curve, we could find distance and even because even what I thought, and I guess it doesn't make sense. How would the area under the curve? That's a good question. For whatever reason, I was thinking the area under the curve would have given us the velocity, and wouldn't that be the case if this was acceleration on that axis? So we're going to go meters per second, and then we're going to have time on this in seconds. So if we have like whatever, you know what I mean, if it looks like our acceleration increases, start at 0 acceleration, then increase, the area under this curve is going to give us an average acceleration from this time to this time. And yeah, let's see what the units would be. It would be 1/2, because we're going to try to find the area of the triangle, which is 1/2 the area of the rectangle. And this is going to be meters per second. That's the units on this side, and then we're going to multiply by time. That's in seconds. Times cancel, and heck yeah, we get a value of velocity. You know what I mean? That actually would give us our velocity. It would our average velocity. You know what I mean? So this is the area under the acceleration curve with respect to time. The area under that for any given chunk of time would give you the velocity average over that chunk of time. You know what I mean? And that's what I thought we were dealing with. So now I'm scratching my head because it seems like this problem is going to be a little bit harder. All right, so let's start looking at the problem. You know what I mean? It says the average, the distance s traveled by the point as a function. Yeah, so this is the distance traveled by the point. Okay, so this is the total distance. You know what I mean? So this is very interesting. You know what I mean? Because the total distance it travels is 2 meters. You know what I mean? So there you go. So it says at time 20 seconds, it's 2 meters away. That's basically what that says. And you know, the first equation that I'm definitely going to write down all the time is average velocity. It's very important because average velocity is distance total divided by time total. And so even here, we kind of want to know what the average velocity is. That's an important parameter, and it's going to be 2 meters divided by 20 seconds. Man, whatever this thing's moving, it's moving snail pace. You know what I mean? So 2 divided by 20 is going to be a velocity of 0.1 meters per second. Now, what's 0.1 meters? That's always a tenth of a meter. You know, you should know that 1,000 millimeters is a meter, and then so a tenth of that is 100 millimeters. So that's 4 inches. So just getting a representative of hey, this is about 4 inches. You know, I mean, we got about 3-4 inches across here. So this particle, if its average velocity is just going to be just average, we're going to go from like 0, 1, 2, 3. So every second it went 4 inches. Every second it went 1 meter per second. It's just, you have to do problems in European units, you know, meters per second, but it's just nice to have some sort of relationship to Americans so you can be like, okay, I got a visual on this. You know, it's moving slow, but you know, I mean, that's how slow it's moving. But check this out. We know that at some point it's moving 0.23 meters per second. So at the fastest, it's going, let's say let's say it's going, because even this, I know that 200 millimeters is, you know what I mean, 2 times 100 millimeters, and I know that 100 millimeters is 4 inches. So this is 8 inches, but plus another, you know, 30 millimeters. And you definitely have to know that 25.4 millimeters is 1 inch. So this is going to be 8 plus 1. It's going to be 9 inches. So there you go. At the fastest, we're moving 9 inches per second. So that's almost this whole page. So it's like 0, 1. So there you go. So, and where on this graph are we actually moving 0.1 meter per second? You know what I mean? Can we even find that using the slope? The slope says we're going to go up 0.1 and we're going to go over 1 second. Now, our graph isn't in 0.1 meters up. It's in 0.2. So, but we can still say the slope of this is going to be 0.2 meters up per 2 seconds. See how the slope here for our average velocity is the same as 0.1 meter per 1 second. These are the same. So wherever we can find that we go up 0.2 meters, but we go over 2. So yeah, so it looks like right there, you know what I mean? Right there's a pretty good representation of going up 0.2 but over 2 seconds. And where else? So right here almost, you know what I mean? Because here is too steep. That's almost twice. Like right here. So now we're getting an understanding of the graph. Like hell yeah, right there it looks like we go twice. Looks like we went 0.2 meters, or now that we got a good representation of this, it looks like we went 8 inches in 1 second. You know what I mean? Whoa, okay, so right there we went 8 inches in 1 second. And, you know, just to check on reality, didn't we say the fastest right here is 9 inches per second? So yeah, that's pretty wild. So here to here, for sure, we might be going 9 inches per second. But if at any one of these looks like we're going, you know, up 0.2 meters and then over 1 second, hell yeah, that's 8 inches per second, moving 8 inches per second. Cool. Now we kind of, you know, now we got a really good understanding of this graph, and it all started from like not even knowing what the hell this graph was and thinking we were going to integrate. But anyway, so cool. And then I'm sure we're solving the problems just by kind of understanding this graph. You know what I mean? I think like figuring out what they're asking and then scratching your head is like the worst way to start a problem. First way is just like, cool, I have this graph. Let's say I'm just going to, it's like a Rubik's Cube. We're just going to play around with it all day and at least do the basics. You know what I mean? Move some colors. All right, so yeah, so those were the 2 places where we actually see average velocity. I'm just going to mark those, you know what I mean? Because like right there we got V average. And definitely right here we got V average. That's pretty cool. And that means that down here it's like, whoa, we're going way slower. You know what I mean? So let's just pick the halfway point, and we can see that, you know, even right here, look at this. It looks like we're only going up a quarter of a square, but we're going over 2 inches. So we're not even going up 0.1 per 2 seconds. We're going up 0.05 in 2 seconds. You know what I mean? And so another way to represent this is is, hey, this is the same as going up 0.1 meter in 4 seconds. You know what I mean? So now you kind of see that relationship. If you're just like, hey, how far are we going? Well, we're going to go 4 inches because 100 millimeters is 4 inches. So 4 inches in 4 seconds. So if this is 4 inches, we're going to go 0, 1, 2, 3, 4. So yeah, so right in here, that's the speed of our particle. That's pretty wild. And then right in here again, it's 0, 1. You know what I mean? We're going a full 9 inches for that. And it's even worse. So for the first 2 seconds, that's only the speed for 2 seconds. So if I said our speed for over 4 inches is like 0, 1, 2, 3, 4, we're only doing that for 2 seconds. So we're going to go 0, 1, 2, and then we're going to increase our speed a little bit. And then in this section, we're going to go hella fast. So right here, like this is probably the slowest. And it looks like we're only going to go up a quarter of in 4 seconds. So we're going to go 0.05 meters in 4 seconds. That's 0.1 meter in 8 seconds. So that means that we're going this whole distance in 8 seconds. So we're going to go here in 4, here in 2, here in 1. So we're going to go 0, 1, 2. But we're only going to do that for 4 seconds. So we're going to go 0, 1, 2, 3, 4. And then we're going to slowly increase. Then we're going to go 0. And then we're going to go basically almost twice the speed. I mean, we're going to go this speed, 0, 1, 2, and then we're going to go twice the speed, 0, 1, 2, and sweep. And you can see that this is fairly slow. Once we go fast, then we quickly come to a stop a lot faster than here. So this part of the curve kind of looks like this part, and it even slopes like harder. It basically goes from here to there, and so after this peak velocity, we stop definitely faster. All right, so let's start to answer some of the problems. The average velocity of the point during the time of motion. So so use the plot to find the average velocity. Didn't we just do that? This is a really important equation, you know what I mean? And I used the grocery store analogy in the other video. Is like if I see someone at the grocery store, and then 2 hours later I see them at the bar, and I know that between the grocery store and the bar is 10 miles, and so and what's the average speed? We use that equation that the average speed is the total distance. That's 10 miles. So we have 10 miles and divided by the total time. That was 2 hours. It's kind of a bizarre one, but hell yeah. So we have 5 miles per hour. That person, their average velocity was 5 miles per hour, even though they're still just walking around aimlessly in the grocery store, walking through the parking lot, and then they get in their car and drive real fast. Maybe in in whatever direction, we don't know, but maybe their house is, halfway between there and the bar. And then they go to their house and then just chill out, make some dinner, and then they drive real fast to the bar and then walk to the bar. And then I see them. You know what I mean? It doesn't matter what they did in between. I know their average velocity. And the cool thing about that is that if I know their average velocity, this is a product of velocity. Unless they were just going 5 miles per hour from the time that I saw them, and were just, this time that I saw them in the grocery store, they got freaked out and they're just like, I'm out of here. And then they just start walking 5 miles per hour, which is a pretty brisk pace, and they get to the bar. And then 2 hours later, I see them at the bar because they just walked with brisk pace to the bar side, and then I'm already at the bar, and then I see them, and then they freak out. You know what I mean? Because they see me again. Their average, their speed was 5 meters per second. So I guess what I'm getting at is we know that they probably are going slower because they're walking around the grocery store slower. I should just spell it out. So average velocity means that even if they went slower or took breaks or just went constant speed, there's always going to be one location where they're going the average velocity. And maybe there's 2 locations, because even right here we found 2 locations. So maybe that's an axiom. If you're ever going slower, so in this case, They take their time, go to the parking lot, and then drive home. In that drive, they're definitely going faster than the average velocity, and that's the first time they actually go through the average. They're slower than the average, go through the average velocity, and then they're super fast. They get to their house, and let's just say they like they spend an hour in the grocery store almost, and then or like almost 2 hours in the grocery store. Yeah, let's say, because I see them 2 hours later. So let's say they spend almost all of that 2 hours, minus a few minutes, and then they just like, oh, I got to get to the bar. And then so in that time, they're going to pass this average velocity of 5 miles per hour. And then once they hit that peak or whatever, then at the bar, they got to slow down. And so they're going to go through that average velocity again. So that graph will look like that. And I think that proves that as long as you're not going a constant speed, and if I can observe that at your initial speed was less, if your velocity initial was less than the average velocity that I calculated because I saw you at the grocery store and in the bar 2 hours later, then I know that you had to go through that's a weird one, you know what I mean, kind of creepy that I know something about you, or I don't know why I'm making it creepy, but anyway, so I know that person went through that velocity zone twice. That's very fascinating. And they could go through that velocity zone a lot of times. If they get into their car, stop at a stoplight, they're constantly going from 0 through that velocity zone. But just from an overall perspective, I think that's fascinating. That's a fascinating proof that they have to at least go through that zone twice if they start with an initial velocity that's less than their average. All right, hell yeah. So it says, what the hell does it say? It says find the average velocity of the point, and I guess they're just saying a point. It's a massless point. They have to do that. It moves rectilinearly. I had to look that one up. This part, rectus, is a Latin for straight, and then linear, that's the Latin for line. So straight line. I think it's almost redundant. You know what I mean? Well, no, because if you have a linear. This is like I was asking my brothers, like, well, what should I study to learn quantum physics? What's some good building blocks? And he was saying linear algebra, and all I could think of was like straight line of like a constant or something. I don't know, but no. Linear, like is any sort of line, and then I was just like, so does linear just mean two things, non-discontinuous and stuff that doesn't wrap back around itself, you know what I mean? So you have linear algebra, because a lot of quantum physics is finding probabilities where you have a slope curve with the area under it always equal to 1 squared or something, or just 1, or however that works. But anyway, that's a little tangent. So what are we doing? We're finding the average velocity of the point. We learned about rectilinear, and we learned about linear equations. So the average velocity, we already did that. But it's a good equation. It's the total distance divided by the total time. All right, so what's the maximum velocity? I think we found that just from the graph. It was 9 inches per second. In meters per second, that was going to be... I don't know why I did the vibrato. Holy Toledo. So that was, it's 1.4 meters in 6 seconds. So we got 1.4 divided by 6. And maybe I'll do a better job of actually putting the answers down here. So average velocity, wasn't that 0.1? 0.1 meters per second, or that kind of 4 inches per second. And again, we moved 2 meters in 20 seconds. Yes, that's 0.1. This max velocity is going to be, it's 0.23 meters per second. Cool, hell yeah. And then the time moment, what? Like, this is so, everything in this book is just weird. It's just, are they talking about like a moment, like a force times distance? Because if I have like a wrench, you know what I mean, and I'm wrenching on something, this is the force, this is the distance. That's the moment of force, you know what I mean? So what the hell is the moment of time? You know what I mean? I would have some sort of time out here and then some distance away from it. Are they literally saying, the moment of time is time times distance? This is bizarre to me, because what would time and distance be? That would be seconds times meters. So they're obviously not saying that. So the time moment, are they just saying the same thing twice? I have no idea. The time moment T naught, at which the instantaneous velocity is equal to the mean velocity. I have a hard time reading this, but is equal to the mean velocity averaged over the first t naught seconds. Isn't t naught always supposed to be like 0? Like the, okay, the time, like or moment or something or whatever, t naught. Okay, so the time, so you just pick a time. How about right there? At which the, how about right there where the instantaneous velocity is average? Is that what they're just saying? Didn't we pick that twice? So the time or moments, it should be plural, at which the instantaneous velocity, hell yeah, we already found those points, it is equal to the mean, and I swear I barely read this problem, because, and you can tell that because I thought we were going to integrate under the curve or something. But it's just fascinating. You play around with something and you just solve everything, you know what I mean? So yeah, the instantaneous velocity, hell yeah, is equal to the mean velocity, and mean is just that average velocity. We already found that. And arranged over the first t naught second. I hate this, man. The time, moment, t naught, at which the instantaneous velocity is equal to the mean velocity. But then this part, averaged over the first... Oh. So they don't want the instantaneous. Okay, so here, what's the slope on the average velocity? It's going up 0.1 meters and then over a second. Or we already said that it's also going up 0.2 meters in 2 seconds, because that's more representative of a graph. We're going to go up 0.2 and then over. So what they want is, like, if we start from t naught, t0, where on this do we go up and then over the same amount? So here, let's just try it. We're going to go up 2 and over 2. Hell no, we're not on the graph. Up 3 over 3. Nope. Up 4 over 4. Nope. Up 5 over 5. 1, 2, 3, 4, 5. Hell no. Up 6. 1, 2, 3, 4, 5, 6. Nope. Up 7. 1, 2, 3, 4, 5, 6. And am I even counting right? 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Hell yeah. So there you go. I'm glad I read this a billion times, because that was not easy to figure out what the hell they were talking about, because it sounded like there was only one moment. They didn't pluralize it. And it was just cool that we found these other moments that we went through the mean velocity. That was a better question. But there you go. So they're saying that over this time, even though we're going hella slow, but then we're going to go hella fast, this is equal to our average velocity. So if we just did this for 14 seconds, then, and this is the cool thing. This is the cool thing about this, because it's just like, well, isn't our average velocity this entire... Aren't we just going this average velocity the entire time? Sure, look at that. So we actually hit this point. So you could say between this time and this time, we're going an average velocity. So that is fascinating. And what this kind of shows something different, because it shows you a time where you actually go not the average velocity, but it's where like you're like you're not going through, like our question was like, hell yeah, you'll go through the average velocity twice. But I'm sure this is also an important representation. Because let's say I do just go hella slow, get in my car. Alright, so actually before we figure out what this actually represents, we at least need a time on it. They're saying the time is going to be 14 seconds. So there you go. So you got 14 seconds. So there's one answer, there's another answer. And we're done. But yeah, this is fascinating to me. Like, how could I set this problem up where, you know what I mean, hey, we just spend forever. So if this is 2 hours, you know what I mean, we're saying this is 2 hours. It's not the distance to the bar, but if we're saying we're literally spending all our time at the grocery store, and then all of a sudden we have to drive to the bar, and so and actually it looks like this, you know what I mean. Let's say hey, we get into our car and we just hit the freeway and then stay 60 miles an hour on the freeway, get off the freeway, and then the bar is just right there. So now, from this perspective, Whoa. No. We would have to make the graph look like that. So let's try it. Let's try it. Because here's our distance. Here is the 10 miles to the bar. And here's our time. And here's so we're just at the grocery store. And then all of a sudden we're like, holy Toledo, I've been talking, at the grocery store or something. So I need to, my velocity starts to increase. We get into the car and then it starts to really increase. We hit the highway. Hell yeah. So now my velocity, and this line, this constant line is like 60 miles per hour. And then we, get off the freeway and then the bar is just right there. Okay, so now in this case, this is our average velocity. This is fascinating to me. And so there you go. There's our average velocity. I mean, we just didn't leave the grocery store. But what this is saying is a time right there is where we, I'm still not understanding the moment at which the instantaneous velocity is equal to. Yeah. So this instantaneous velocity is also secondary to the problem. Because if we go back to the problem, this instantaneous velocity, well, let's figure it out. It looks like we're going up 0.4 meters in just 2 seconds. This is a second, that's a second. So we're going in 2 seconds. So we're going 0.2 meters in 1 second. Again, that's about 8 inches per second. So, so I would say the time moment at which the instantaneous velocity of 0.2 meters per second, that's the instantaneous velocity, is equal to the mean velocity over the first t naught seconds. And t naught, that value is that 14 seconds. So, the instantaneous, and maybe not, maybe I didn't do it. The instantaneous velocity, so it's the time or moment where the instantaneous velocity is equal to the mean velocity. I think this is more complex. I think we've solved two things that are not even this question. They want to know the time where this instantaneous velocity is equal to the mean velocity averaged over those seconds. So we are saying at that point, no, the average velocity was 0.1 meter per second. We already found that. But the instantaneous velocity right there was 2 meters per second. So it is these points, you know what I mean? So right there, so I apologize about that, but right there is the time where the instantaneous velocity is 0.1 meter per second, you know what I mean? Or like right there, I guess. And we need a new graph, so let's let's grab a new graph, and what we're going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, no, we can just do this. So the velocity average is distance total, time total, and that's going to be 2 meters over 20 seconds. So that's going to be 0.1 meters per second. Okay. And they want to know, and that's going to be mean velocity. There you go, mean velocity. So they want to know, but yeah, they still, but they're still saying not the mean velocity for the entire trip. Well, this is a bizarre. This is cool because this book kind of challenges me, even if I'm just like not even answering the questions right. What they want to know is like, let's just. Sometimes you just have to guess. So let's just guess right here. So that they're saying, hey, what is that? That's the mean velocity in the first 10 seconds, and that's going to be up. And I got to get 0.2, 0.4, 0.6, 0.8, 1.2, 1.4, 1.6, 1.8, and this is going to be 2, 4, 6, 8, 12, 14, 16, 18. All right, so the mean velocity, and what's the way to write mean velocity? I don't know. I'm just going to do a little squiggly. You know what I mean? That's different than this average velocity, but the mean velocity of this is going to be 0.4 meters in 10 seconds. And I brought this up in my other video. Is just like, I call this juggling. You know what I mean? We're just throwing one ball up and then catching it. You know what I mean? And this is where we're going to be. Sometimes you can have two. You know what I mean? You can throw one ball up in that hand and then catch it and then throw the other ball up in that. You know, so math is juggling. Sometimes you can do like, you know, all over your head and then cool. But we're just gonna the throwing numbers at something is just like, hell yeah, throw one ball up, catch it. All right, so we have so this is going to be 0.4 divided by 10, 0.04 meters per second. That's the mean velocity right there. And what's the instantaneous velocity? Well, it looks hella, you know what I mean? So even just right there, if we drew, and we can get into it, you know what I mean? Draw some straight lines, draw some tangents. I'd say that's pretty good. So we're just going to draw a little tangent. And hey, look at that. We go up 0.4 over 2. So up 0.4 meters over 2 seconds, that's going to be 0.2 meters per second. So obviously those two things are not the same. The mean velocity was 0.04, and then the instantaneous velocity was 0.2. And this question says, hey, instantaneous velocity literally equal to that mean velocity. I'm going to say squiggly. So I would think we just have to come down, you know what I mean? So I'm just going to go... and honestly, let's just go to that point right there. So I'm going to say that looks like 0.0. So if this is 0.1, that's 0.05 meters. And it looks like the mean velocity squiggle is 4 seconds to do that. So 0.05 divided by 4, and we get 0.0125 meters per second. And now we can just figure out what that is, because we can just say, hey, multiplied by 20 seconds, we're going to go up 0.25. So even just to figure out what the slope of that line is, and I guess it makes more sense to start there. So we're going to start there and then go to here, and we're going to go up 0.25. So we know that one of these, I'm just going to say up 0.2 and then 0.25, but then we got to go back down to there. So wait, did I do that right? So if we start here, if we start here, we're going to go 2 to 2. Yeah, we're going to be right there. So that's going to be the slope. And is that pretty close? Well, look at that. That's pretty damn close. You know what I mean? That slope looks like here, and then we got a value of that. Yeah. And they're saying over the first second. So, yeah, I would say that's pretty damn close. I think we did a very good job, because this chart is so small. It's like, how are you even going to see that? So I'm just going to call it good right there. So I think we found the time where the instantaneous... So let's just throw a tangent on this, and then we'll measure it and see if it's... I'm just going to undershoot it just a touch, because that'll help my guess. And... okay, so we got a line on that, and now we can see, hey, it maybe starts right there, and where does it hit? Oh, there, it hits there pretty decent, and so we're going to have 22, 24. So we're going to have 22 seconds, and we're going to go up a distance of 0.4. So 0.4 meters divided by 22 seconds, 0.4 divided by 22, and we get 0.018. And, oh, so that was still too much, you know what I mean, because, alright, so, yeah, that was still too much, because the mean velocity, you know, the v squiggly, if that's what we're calling it, was, you know, hey, this is 0.1, and it looks like this is 0.5, but 0.05. But let's say this was just 0.04, and we just interpreted wrong, and so we're going to say 0.04 in 4 seconds, 0.04 divided by 4, and that gives us a squiggly mean velocity of 0.01 meters per second. And then our guess was 0.018, which is overshot. Oh. So yeah. So we're going the wrong direction. So yeah, we definitely need. So yeah, let's go to 5 seconds. You know, at least do that one. And this at 5 seconds, it almost looks like a third. I would say that, or like 0.4. I'd say we go and it's not 0.4, but it's a third. Wait. This is 0.1, so we're going. I'm just saying right there. It looks like a 0.4 as a fraction of 0.2 meters. So if we have 0.2 meters times 0.4, so I'd say we're going 0.08 meters. And in here we were only going 0.05, so that's a check. And it looks like we went 5 seconds. So we got 0.08 meters in 5 seconds. Divided by 5, hell yeah. So we get this, and this problem sucks because you're just dealing with small numbers that are meaningless. And we could do this, 0.016. We could change this to millimeters per second. That would be 3 decimal places, so we're going 16 millimeters per second. And we know that 25.4 millimeters is 1 inch, you know what I mean? So 16 divided by 25.4, hey, that's about 3/4 of an inch. I'm just going to say that's this distance. So our speed for that particle is like 0, 1. You know what I mean? So that's the speed, 0, 1, right there. so that's 0.016. So this is the mean that's the mean velocity. If we draw a line from 0 up to that, that's going to be, and the mean velocity is just the localized average velocity. You know what I mean? So we're saying that the total distance to that point that we traveled was 0.08 meters divided by the total time to that point. You know, so it's very similar to the average velocity, but we're saying it's the mean velocity because it's the distance to t naught, that point at that, and then t naught's right here. So the distance to, you know, if we travel t naught, what's our distance, and then divided by that actual time. And it was 5 seconds, and we get 0.016 meters per second. Cool, so that was the instantaneous velocity. We're going to, hopefully we overshot this time, and we can be done with this video. So we're going to draw a line right there. And now, it's just really good practice to be like, okay, that's halfway. That's a pretty good place to take a point. Hey, that looks pretty close to right there. You know what I mean? So I'm going to say, you know, we went 0.4 meters. That's this rise. And then in run, it looks like we went, this is 22, this is 23. So 23 seconds. So 0.4 divided by 23, and this is 0.017 meters per second. Hell, that's close enough, and I think we did it. And I'm going to say the timer moment is 5 seconds. And so now we have a full check on reality that A is 0.1 meters per second, maximum velocity 0.23 meters per second, and the time at which the instantaneous velocity, you know what I mean, we did the tangent to do that, is going to be equal to the mean velocity, you know what I mean, the distance traveled in that amount of time. Cool, and that was equal to 5 seconds. That's the time. T naught is 5 seconds. Maximum velocity, Vmax, is that. And then the average velocity, there you go. So sweet. You know what I mean? That was pretty good. I'm pretty satisfied with this one. And for this video, you know, I don't have to do an intro. I think this video stands alone where you can just watch the whole thing through, get the numbers. It doesn't need an intro after just, you know, suffer-festing through a long one. So yeah, we did pretty good on this one. And it was just so fascinating that at the beginning I thought, hell yeah, we're totally going to find the area under the curve. But no, we identified what our y and x axis is. And again, calculus, you can only do 2 things. You can take the area under the curve, or you can take the rise over run. And then just throw units on those, because our rise over run gave us meters per second. That was hella. But if we took the, I'm just going to say one more thing and then we're done. If we took the area under the curve, we would have meters times seconds, and that's just a nonsense term. So hell yeah. So we knew that was a mistake, and then we knew this equation. That's when I knew this problem was just going to be a lot harder, because you have to deal with slopes, and look at all those different slopes. They're all over the place different. Okay, so thanks for joining me, and that's a video.